This lesson will focus on the characteristics of a parabola, such as determining whether the opening faces upward or downward, identifying the vertex of the parabola, identifying the axis of symmetry, the domain and range, and identifying the x and y intercepts of a quadratic function.
A function is a quadratic function if, in the form of standard form ax squared plus bx plus c equals 0, where a, b, and c are real numbers, with a not equal to 0. Regardless of what form the equation is in, whether it's in standard form or vertex form, or factored form, as long as out of all the terms the highest degree is a degree of 2 or a squared term, then you have a quadratic function. The graph of a quadratic function is a U-shape, and it is called a parabola. So if an equation is in standard form, the coefficient of the squared term will determine the end behavior or the shape of the U in terms of facing upward or whether the U shape will be facing downward. So if A is greater than 0, then the parabola would be facing upward. Notice here we have the parent function x squared. The coefficient of the squared term is a positive, so therefore the parabola will open upward. And if a is less than 0, meaning a negative, then the parabola will open downward.
Whether a parabola is facing upward or downward, the vertex is the highest or the lowest point on a parabola. Now at that highest or lowest point, which is called the vertex, you're going to have either a maximum or a minimum point on that parabola. So if the parabola opens upward, you're going to have a lowest point, which is called the minimum. And if the parabola opens downward, you're going to have a highest point, which is called the maximum. So of course, if you are given a graph of a parabola, you can determine easily whether it has a maximum or minimum point by simply just looking at the shape of the graph. Opening upward would have a minimum and opening downward would have a maximum. Now, if you're only just given the equation or the quadratic function, then you're going to look at the coefficient of the squared term, which is called a, to determine whether it has a maximum or minimum point. If the coefficient of the squared term is greater than 0, meaning a positive, then that means that yes, it opens upward and then you're going to have a minimum. However, if you notice that a is less than 0, meaning a negative, then that means the parabola is going to open downward, and then so you're going to have a maximum point. Parabolas are symmetric with respect to a line, meaning that you can draw a vertical line through the middle of a parabola, and it sort of splits the parabola into two equal parts. Now this vertical line is called the axis of symmetry, and it goes right through the vertex of the parabola. When you are asked to identify the axis of symmetry, it is not merely just stating a number, but rather you are stating the equation of the line. You are stating the vertical line which passes through the vertex center. So let's take a look at the first example. We want to know what is the axis of symmetry. So if we were to visualize that vertical line that goes right through the parabola, that would be a line going through at 1. And so to write that line in equation form, the axis of symmetry then would be x equals 1, meaning it is a line passing through the x-axis at 1, and you have to actually state the line. So what is the line or the axis of symmetry for the second example here? If you notice that the line went through 0, the origin there, then yes, the line would be x equals 0. And that is the axis of symmetry. Here is the vertex form of a quadratic function. If a, the coefficient of the squared term, is greater than 0, the parabola will open upward. And if a, the coefficient of the squared term, is less than 0, a negative, then the parabola will open downward. The x and y of the vertex is the hk that you see here in the formula. H represents the x value of the vertex, and k represents the y value of the vertex. In this example, we're asked to use the given equation to describe the graph of the parabola. We're going to start by identifying whether the graph will open upward or downward. So recall, when it's in vertex form, if the coefficient is a positive, then the parabola will open upward. And when you don't see anything out, then it is assumed to be a positive. If you see a negative, then it is a negative. So again, in this case, it is a positive, so therefore it will open upward. What is the vertex? So recall HK is your vertex, and remember that H horizontally, it is not always as it seems. So even though you see the negative here in H, it means that the value H is actually positive. So in this case, our X value is a positive 4. Now, the Y value is in the back, and vertically it is always as it seems. So if you see a negative 3 in the back, then that is the Y value, then is negative 3. So the vertex will be located at 4, negative 3. If we were to graph this, just looking at the transformation of it, we can see it is nothing more than the quadratic function that has been shifted to the right 4 units and down 3 units. So if we graph it, it's going to look like so. And notice the graph will shift over 4 units to the right and then 3 units down. Okay, so how about this next example? Looking at the quadratic function there, we can see that the coefficient of the squared term a is a negative, less than 0, which means that this parabola, yes, is going to be facing downward. What is the vertex? Well, if we look at the vertex, remember H and K, and remember H is always not what it seems, it's always the opposite. So for example, you see +2 here. the value of h is actually -2. In the back is your k, or vertical, and that's always as is, and that is +4. So our vertex then is -2, 4. In terms of what that look like, we can look at the equation itself and see the transformation here. Not only was it flipped across the x-axis, but in addition to that, horizontally, it was shifted over to the left 2 units, and then up 4 units. So when we graph it, it's going to look like so. Notice the graph was flipped across the x-axis, moved over 2 units to the left, and then 4 units up. In this example, we're asked to not only graph the given equation, but also identify certain characteristics such as the domain, the range, the vertex, axis of symmetry, and the x and y intercepts. So let's first proceed by taking a look at what this graph would look like. So looking at the equation here, we can see that there was a horizontal shift there of 5 units to the right, and then 4 units down. So when we graph that function, it's going to look like so. Next, we want to find the domain of this function. So recall the domain, if you look at it algebraically, you just want to know all the allowable values of x that you can plug into the function. If you're looking at the graph to identify the domain, you want to know how far that graph extends both to the left and to the right. And the fact that we have arrows on both ends of our graph means that it is going to go forever and ever to the left and forever and ever to the right. So therefore, the domain then would be from -infinity to +infinity. All right, let's now determine the range. The range, on the other hand, we want to know, excuse me, the lowest point on that graph and the highest point on that graph. So what is our lowest point? Well, you can just look at the graph and you could be able to identify that the lowest point on the graph would be right there at -4. Recall, when a parabola opens upward, it is going to have a minimum, a lowest point. And that lowest point is the vertex. Now, in terms of identifying the range, we want, yes, the lowest point, and that's at -4. And now what's the highest point? Well, again, because we have arrows on both ends, it's going to go forever to +infinity. So therefore, we would say that our range would be from -4 to +infinity. What is our vertex? Well, if we look at the lowest point again on our graph, our lowest point there is right here at over 5 and down 4. If you look at it algebraically, notice here that our value, x value, is 5. Our y value is -4, so our vertex is 5, -4. What is the axis of symmetry? In other words, the vertical line that passes through our vertex. If you said x equals 5, then that is correct, because that is the vertical line that passes through this particular function. Now we want to identify what the x-intercept is. Recall the x-intercept is the point where the graph touches the x-axis. We can just look at our graph and be able to readily tell what our x-intercept is. Our graph touches at 3 and at 7. So therefore, the x-intercepts are located at 3, 0 and 7, 0. Now, if you were not given a graph and you were asked to identify the x-intercept of this function, to recall to find the x-intercept algebraically, you have to let y be 0 to solve for x. So you should know that f of x is the same thing as y. So let's go ahead and make that 0 so that we can solve for x. Now the first step to doing that, we need to get the squared term on the side by itself and the constant on the other side so that we can utilize the square root principle or the square root property. So let's go ahead and add 4 to each side. Our next step is to take the square root of both sides. When I do that, that's going to allow me to bring x minus 5 down by itself on the left side, and on the right side is going to equal plus or minus 2. Remember, when we're using the square root property, we have to include that plus or minus in our answer. Last step to solving for x is to do what? Yes, we've got to add 5 to each side. And once we add 5 to each side, we're going to have 5 plus 2 and 5 minus 2. And those two values are 3 and 7, the same answer we got from just looking at the graph and identifying the x-intercepts. Now we want to find the y-intercept. So with the y-intercept, looking at it visually, we can see on our graph that if we were to extend the left arm there of that parabola, that it will eventually touch the y-intercept, but it's going to touch it way up high at a point where our graph right now is just not big enough to see that value. So we're going to have to find it algebraically. And when you find it algebraically, to find the y-intercept, you have to let x be 0. So in the original equation, we're going to remove x and replace it with 0 and do the math. So now that we've removed the x and replaced it with 0, let's do the math. Negative 5 squared, that's negative 5 times negative 5, which is 25. 25 take away 4 is 21. So when we plug in a 0, what we get out is a 21. So the order pair 0, 21, which means yes, at the y-intercept, it's going to touch way up there at 21. So notice I drew another graph there where the y-axis there was extended so that it would include that number there of 0 and up 21. And as you can see, yes, that is the x-intercept. In this example, we were given another equation and asked to identify certain characteristics of that quadratic equation. So starting with just how the graph looks, it looks like as far as the transformations, this graph was reflected about the x-axis as stretched by a factor of 2. Also here, we noticed that horizontally it was shifted to the left 3 units and then up 2 units. So once we graph it, it's going to look like so. What is the domain of this quadratic function? Well, notice you have arrows there on both ends. So in terms of the domain, how much it extends to the left and to the right, it's going to go forever and ever to the left and forever and ever to the right. So therefore, the domain is from negative infinity to positive infinity. Now, in terms of looking at it algebraically, what are all the allowable values I can plug in? You can plug in any number into this function, and you're not going to violate any rules or anything. So again, it's from negative infinity to positive infinity. How about the range? Recall the range is we want to know how far this graph extends both up and down. Well, again, because this parabola is facing downward, it's going to have a maximum value. So the highest point on this graph is going to be at 2. In terms of what's the lowest point, well, notice that you have arrows there on both ends. And so that means that this particular range here, it's going to go forever and ever down to negative infinity. And so how would we write that? Well, we would start with our smallest number first. So coming from negative infinity, you would go parentheses, negative infinity, comma, stop at 2, and we're going to use a bracket there at 2. So the range, again, is from negative infinity to 2. All right, next we want to focus our attention on the vertex. Where is the vertex? Well, you can look at the graph to easily see where the vertex is. It's going to be at that maximum, that highest point, and it's right there at the center, the middle of the parabola. You can look at it algebraically and see that our x value is going to be -3. And that our y value is 2. That's the same as if you go over to your graph and go over -3 and up 2 is where our vertex is located. Next, we want to identify the axis of symmetry, which is the line that passes through the vertex. And where would you say that is? If you said x equals -3, yes, that is the vertical line that would pass through our parabola. And again, the equation of that line is x equals 3. Always write it as an equation. Next, we have the x and y intercepts that we want to identify. Remember, if you have a graph, sometimes you can see those things. The x-intercept would be the point where it touches the x-axis, and the y-intercept would be the point where it touches the y-axis. Now, if you can't see it on your graph, then you're going to have to find it algebraically by plugging it into the equation. So if you want to find the x-intercept, you have to let y be 0, and if you want to find the y-intercept, you let x be 0. So starting with the x-intercept, since we can visually see that on our graph, that our graph touches the x-intercept at -4 and at -2. So that is our x-intercept. Now, if you did not have the graph and you wanted to know just based on finding it algebraically what the x-intercepts are, again, you're going to let y be 0. So if you remove f of x, replace it with 0 because f of x is the same thing as y, and now solve for x. To do that, that would mean I need to subtract 2 from each side. Then to isolate the squared term, I need to divide by -2. Whatever you do to one side, you do to the other. Once we cancel those -2's on the left side as well as on the right side, what we're going to be left with is x plus 3 squared equals 1, because the right side, a negative divided by a negative, equals a positive. Our next step to solving this is to take the square root of each side. Once I do that, that's going to allow me to bring x plus 3 down by itself on the left side. And on the right side, I'm going to have plus or minus 1. Last step to solving this is to subtract 3 from each side, and I'm going to have negative 3 plus 1 and negative 3 minus 1, which again gives me those two values of negative 4 and negative 2, just as you see on the graph. Now to find the y-intercept, recall you're going to let x be 0, so remove the x from the original equation and replace it with 0. Let's do the math. Inside we have 3 squared. 3 squared is 9. 9 times negative 2 is negative 18. Negative 18 combined with a 2 is going to give me negative 16. So plugging in a 0, you get out a negative 16, which means it's going to touch the y-intercept way down at negative 16. Now you were not able to see it with the graph that I have here because obviously the scale for the y-axis is not long enough to cover that. So I will show that on the next page. But that is how you find it algebraically. Let x be 0 and then solve for y. So this is what the graph looks like once it's graphed. And there you have it.